underestimate non-humans. But you understand this idea that not anything goes. And once you've done that, you have principled means of extracting from the data appropriately normalized conditional probabilities. So think of this, if you like, within the class of graphical models, but with some variance, where we try to calculate causality in a way quite different from Krakauer and others. But essentially it's in that space. We're trying to reconstruct a directed graph which doesn't factorize into individual decisions, where there's some requirement of coordination. And again, I mean, you want to understand the details of this talk to Jess. She'll be happy to do that. But the key here is that what we do, given these elementary motifs, which are these 1, 1, 2, 1, 5, 6, if you like, rules, is we now then concatenate them or compose them into a circuit. Right? So now, if you like, it depends on the kind of circuit. Each vertex is an individual. The edges of the individual influencing the incoming edges, and the outgoing edges of the individuals that I then influence at the next point of time. So this is an aggregate representation induced from the data given the constraint of the Markovian lattice, which is our basis set. And then we use these circuits, we turn them on, and we use them to generate behavior, which we then compare back against the observed behavior. So for example, in this case, the distribution of fights of given sizes in the data. So this is aggregated over all moments of time. It doesn't have the microstructure of the fights. It's another sort of studies that we conduct. And so that's what you're sort of doing. That's the game you play. Highly resolved data, some human-selected basis functions, induction, and then aggregation to produce out-of-sample observables. Now, you could say, well, again, you know, we've got mechanisms, we've got something like an algorithm, meaning the circuitry, and we have an output. But the output now is not correct or incorrect. It's some observable that you can independently generate. Okay? The problem with these things is they're extremely complicated. The contrast with the epigenetic models or the kinase models are, those were simple, individual, trivial collective effects. Lots of kinase enzymes are basically identical, and I can write down a statistical physical model that captures phase transition. Here we have an extraordinarily complicated set of decision rules in a very heterogeneous population that's finite, tons of noise and mistakes. It's not as obvious how you write down the statistical physics model, although we try. And one thing that we do is we say, are we getting the dimensionality of the system right? Maybe not all the individuals are key. Is there a way of compressing the data, compressing the time series into an effective circuit which is more comprehensible? And this is a world that you will be familiar with. It's this world of sparse coding and so forth, where you just have some kind of fit to the data, you have some kind of regularization function which imposes a penalty on the number of degrees of freedom in the data. And we're trying to come up with a compressed circuit that does as well as the observed circuit, recognizing that maybe me, Jess, and Melanie are not actually independent particles, but are coordinated entities in time. So we're not all as individual as each other. Some are more individual than others, to use a kind of definition of Jim. And having done that, you now construct a different kind of circuit where, if you like, the nodes are no longer individual vertices that you know as individuals, but aggregates. And your directed graph operates at a renormalized scale. But it has to perform as well as the higher dimensional graph. And so we're very interested in this idea of highly compressed circuits. And this is something that you don't see so much in the biological sciences, because there is a tendency to be obsessed with particularities, and so that every enzyme matters, and so you get these ridiculogram graphs. But it's a good place to start. We claim that's not wrong, but you need to now do the next step, compressing it down to something that's comprehensible. And maybe that's, by the way, a distinction that we have with computer science and machine learning, because, and I would like to argue this, I think a lot of people in computer science, not microscience, would say human comprehension is a luxury that we can dispense with. Because who cares? And I would claim, as a human being, my existential imperative is to understand the universe. And if I am absolving myself of that responsibility, I'm no longer being a scientist. I'm being the technical support of a system that only cares about controlling the world, which is fine. But I think there is a deeper philosophical debate in here, and I think the business of science is translating the phenomena that we have no control over into the phenomena that we have control over, partial control over in our minds. It's about translation. It's a translation exercise. And if you give up on that, I think you're doing something very different from you, which is fine, but less interesting to me. And so, okay, so that's enough phenomenology. I'm really done. I sort of remind you of the kinds of things that we were worrying about. Stochastic models, dynamics on networks, near critical phenomena. I didn't really talk about it so much, I've lost it, but lots of studies we do on criticality. Some notion of effective endogenous compression. I told you how we do it, but organisms do it all the time. It's like, for example, name your family members. Well, that's a course thing on a kin class all the time. And so do these animals. You preferentially engage in a battle with members of your own department, or I don't know how this is or within your department, and so on. And so this notion of a kind of sparse causality, because of course in statistical notions of causality, since they're not mechanistic, it doesn't matter what level of granularity you describe them not. And what I didn't talk about at all, the other element for us is very important, which is gain structure. Strategic interactions. At the particle level, at the transistor level, right, that they are actually playing a game with slightly different utility functions, and you're looking not necessarily for equilibria, which, as we all know by now, are numerous and probably impossible to find. But we are looking for approximately good solutions in our utility functions. So these are the elements, and I'm going to kind of, am I done? Yes, I'm done. I just want to say that these don't map in any obvious way onto the computing frameworks that I know. Those of us working in complexity science, that some of you are wary of, suspicious of, what is that rubbish? That's sort of what we're after. We're saying, we've been studying the systems, and there are sets of formalisms that don't necessarily cohere, but they seem to be absolutely critical to understand these kinds of things. And we're not really interested in applying a pre-existing framework that came out of recursive function theory that proved to be valuable in proving a proposition of Hilbert. Right? We want our own new frameworks which respect the facts and the resolution of the data that we can measure. And so that's sort of, if you like, a strong case. And whether this amounts to a unified framework, I have no idea. It certainly doesn't do what we've done. But that's the sort of vector that we're wanting to follow. Thank you.
Probably give people a minute for people who need to leave, and then we have time for questions and discussion.
I will.